Hey everybody, this is Mr. Beckstrom, and I received some questions from a student, so I'm just going to kind of go over these. So the first one here says, find the monthly payment R needed to have a sinking fund accumulated for the future value A, the yearly interest rate, and the time are given below. Interest is compounded monthly. So first I just want to reiterate that in order to use these formulas, the compounding period has to be the same as the frequency that we're making this payment, which is the capital R. So if your payment is monthly, then the interest has to be compounded monthly. So the formula for this one is right here. That is A is equal to R, and all of this stuff here, and then we want to solve for R. So really, we can do this a couple of different ways, but the way that I like to do this is to go ahead and solve for R immediately. That means I'm going to divide both sides by this really large number here. So R is going to be equal to A divided by, and then here we're going to have 1 plus R over M raised to the n minus 1 all over R over M. So I'm going to first find out what this A is, and then what I'm going to do is I'm going to divide it by whatever this amount is here. So the A is 2,000, and the amount down here, I'm going to go ahead and put this in my calculator. So it's going to be 1 plus R over M. So that's 1 plus R over M, which is, in this case, 0.05 divided by 12. And then we're going to raise that to the n. Remember, the n is the total number of compounding periods. So if it's 3 years, every month, you're just going to do the number of months in a year times the number of years. So that's going to be to the 3 times 12, which is 36. And enter. And then we can subtract that 1 there. So minus the 1. Enter. And then we can divide that by the R over M. So divided by, and I'm going to put this in parentheses to make sure it does it by the entire fraction. So 0.05 divided by 12. Enter. And now I want to divide this 2,000 by that amount that I got on the bottom there. So I'm going to take the 2,000 and I'm going to divide it by, and I can either type in this whole number here again, or in my calculator I can do second enter, which is entry, and that will, it should, hold on just a moment here. Did I put the wrong thing in here? Let me go back here. I think I hit the wrong button. Clear. So this, 2,000. Let's just type in the number there. I think it pulled up the wrong thing. 38.75333552. And I get $51.61 for my answer. All right, for the next problem, I have 11 raised to the x minus 7 divided by 9 is equal to 23. So the idea for this one is I want to get the term with x by itself and everything else on the other side. So the first thing I can do is just multiply both sides by 9. And what that's going to do is it'll cross out that 9 there, and then I have 11x minus 7 is equal to 23 times 9, which, put that in my calculator, 23 times 9. And I get 207. So this is equal to 207. Next, I'm going to add 7 to both sides. 11 raised to the x is equal to, that's going to be 214. And then in order to get the x out of the exponent position, once I have the term by itself, I'm either going to take the normal log or the natural log of both sides. In this case, I'm going to do the natural log. So the natural log of 11 raised to the x is equal to the natural log of 214. This operation will keep the values of our x. It won't change them. And the reason I do that is because we have a rule with natural logs that say if we have a log with a base to an exponent, we can take the exponent and move it out to the front as a product. So that's what I'm going to do. I'm going to move that x out to the front. So that's x natural log of 11 is equal to the natural log of 214. And then finally, to get the x by itself, I'm going to divide both sides by natural log of 11. And x is equal to this right here. And to put that in my calculator, I can just do it like this. So I can do natural log, that's the ln button, of 214 divided by natural log of 11. Natural log of 11. And there is my answer there. 2.238 if you round to the third decimal place. All right. Okay, this next one says, suppose a woman has decided to retire as soon as she saves $100,000. Her $800,000, excuse me. Her plan is to put $1,000 each month into an ordinary annuity that pays an annual interest rate of 1.8%. In how many years will she be able to retire? All right, so remember, we are going to use this formula here. And we're going to be solving for n. N is actually going to give us the total periods, and then we'll see what we need to do with that n once we get it. But let's go ahead and put everything else in here. So this is going to be the accumulated amount, which is 800,000. 800,000. That's how much we want. Is equal to, she's going to put in $1,000 per month, and then this is going to be times 1 plus our r is, we're going to convert that to a decimal, so 0.018 divided by 12, because remember, it has to compound monthly because the compounding period has to match the frequency in which she puts that money into the account. And this is raised to the n minus 1 all over 0.018 over m. All right, so the first thing I want to do is I want to divide both sides by 1,000. That way, we're trying to get down to this n here. So if I divide both sides by 1,000, 800,000 divided by 1,000 is just 800. 800 is equal to, and on the top, we're going to have, let's go ahead and do that. If I do the 0.018, 0.018 divided by 12, I get 0.0015, and then if I add 1 to that, plus 1 is 1.0015. So this is going to be 1.0015 raised to the n power minus 1 all over, and that's just also going to be, I should have put a 12 over here. Let me correct that. Not sure why I did that. All right. And this will be over 0.0015. That's the 0.018 divided by 12. All right, we're getting closer. Now, remember, I'm working to get this term with the n by itself. So I'm going to multiply both sides by 0.0015 in order to get rid of that denominator, but then I have to multiply this side by 0.0015. So let's see what that is. All right, so 800 times 0.0015 is 1.2. So now we're going to have 1.2 is equal to 1.0015 raised to the n minus 1. And again, we're trying to get this term with the variable by itself, so I'm going to add 1 to both sides. So that's going to give me 2.2 is equal to 1.0015 raised to the n. And then like we did before, we're going to take either the log or the natural log of both sides. This time I'm going to do the log just to mix it up a little bit. But 2.2 is equal to the log of 1.0015 raised to the n. That lets me put the n out front. So the log of 2.2 is equal to the log 1.0015, and the n goes out front. That's why we did the log, so we can pull the variable out front as a product. And then finally, we're going to divide both sides by the log of 1.0015. So we're going to get n is equal to the log of 2.2 divided by the log of 1.0015. Okay, so let's see what that is. So that is the log of 2.2 divided by the log of 1.0015. And I'm going to get 526.03. So this is approximately 526.03. 26. So this is the total number of months. But what are they asking for in this question here? They are asking for in how many years. So how do we convert months to years? We are going to have to divide by 12 there. So if you take that number and you divide by 12, it's about 43.84 years. Let's see how they actually want this one. This is round to the nearest year, so this would be 44 years there. All right. Okay, for this next one here, it says, given a loan amount P, an annual interest rate R, and the length of the loan in years, find the monthly payment R necessary to pay off the loan by completing the parts A through C. Let's do A first. So A is just going to be P, which we know is the 3,000, times 1 plus the R, which is 0.05, because we're converting 5% to decimal, over 12, raised to the total number of periods, so that's 6 years times 12. I think that's 74, but 6 times 12, 72, excuse me. So that's raised to the 72, right? Because there are 72 total monthly payments, because there's 12 payments in a year for 6 years. And then we need to just figure that out. So let's see how we're going to do that in our calculator here. So I'm going to start with the inside function there. So 0.05 divided by 12 is this. I'm going to add 1 to that. Then I'm going to raise that to the 72nd power. And then finally, I'm going to multiply that by 3,000. Remember, we have to do exponents before multiplication due to order of operations. All right, and I get 4047.05. So this is approximately equal to 4047.05. And then we're going to do the second part here, same kind of thing. So let's go ahead and fill in all of our stuff. 1 plus 0.05 divided by 12 raised to the 72 minus 1 all over 0.05 divided by 12. All right, so let's see what this comes out to here. So I'm gonna start up here again. So I'm gonna do the 0.05 divided by 12, and I get that, and I'm gonna add 1 to that from here, and then I'm gonna raise that to the 72nd power. Then I'm gonna subtract 1